Welcome back after the short break. So, we are talking about the CC, and now we will be moving to MOS counterpart. So, in the next slide we will be talking about say common source amplifier. Again, this numerical exercise we have seen before. So, this is the main common source amplifier, and sorry. And then we have the information given here about the device, namely K into W by L, which is 1 milliampere per volt square. Threshold voltage it is 1 volt, supply voltage it is 12 volt, and so and so. And we have seen that using this information we obtain VGS equals to 3 volt, and then IDS we obtain it was 2 milliampere, and then corresponding small signal parameter GM it was 2 milliampere per volt. So, the corresponding voltage gain it was GM into output resistance, and you may ignore the R naught, or rather R naught we may consider this is very high, assuming lambda is very small. So, the voltage gain it was GM into RD, and so that becomes 2 milli into RD is 3 K. So, the corresponding voltage gain it was only 6. So, whatever it is, and then the output resistance for this case we said it is primarily defined by RD, and that is 3 kilo. So, the upper cutoff frequency for this case Fu it was 1 by 2 pi RD into load capacitance of 100 picofarad. So, it was 1 by 2 pi and then 3 K into this one 100 pico, that means 10 to the power minus 10. Yeah. And in fact, if you calculate it, this gives us 530 kilohertz. So, the common source amplifier it is primarily it is having gain of 6, and then upper cutoff frequencies 530 kilohertz. We are not going to calculate the lower cutoff frequency, primarily because our intention here is to see the enhancement of the bandwidth by the use of common drain stage. So, please recall or try to remember this information in our next exercise, where we will be cascading this C stage by common drain stage. So, we do have in the next slide we do have that example here. So, all the informations are we are keeping it same. We do have additional common drain stage coming out of the transistor M2 and its bias circuit R4, and R4 it is given here, it is 1.5 kilo ohm. Note that its biasing it is done directly from the DC voltage available at the drain of transistor 1. So, the DC voltage coming here, if you see the current flow here, it is 2 milliampere, and R3 it is 3 K. So, drop across this 3 K it is 6 volt. So, we can say that we do have a DC voltage of 6 volt coming to the gate of transistor 2. So, we do have R 4 here 1.5 K and its drain it is connected to VDD. Now, how do you find the corresponding current here IDS? So, there is a method. First of all, this IDS flowing through this R 4 creating a drop which is defining the source voltage here. And then at the gate we do have 6 volt, and since there is no current flow, even if you consider the 3 K resistance here, but still we can say that gate voltage it is 6 volt. So, if I consider the loop here, if I consider this loop and if I consider we do have 6 volt coming here. So, we can say that the IDS equals to whatever K W by L by 2 into VGS minus VTH square. And then if I multiply with R 4, so if I multiply with R 4 here, so that gives us the source voltage. But then gate voltage it is 6 minus 6 voltage. So, we can say that VGS minus VTH equals to 6 volt minus this Vs minus VTH is 1 volt. Okay. And so, what is this one? We do have 5 here, and then Vs we do have this expression which is given here. So, we can say directly this is 5 minus R 4 K W by 2 L into VGS minus VT square. So, that is the expression of the VGS we are getting. So, now we do have one equation here which is in terms of VGS minus VTH. So, if we can find the VGS minus VTH, then we can say that we can find the corresponding current. Now, since this equation it is coming primarily in terms of VGS minus VTH, let you consider this is x. So, we can say that this is x equals to 5 minus R 4 it is 1.5 K and K W by 2 L it is 1 milli. So, we can say K and milli they are getting cancelled, and then we do have VGS minus VTH. So, that is x square, right. Yeah. So, we do have by 2 also. Yes. So, now from this one what we can rearrange this equation. So, that gives us in fact 3 x square plus 4 x minus 20 equal to 0. So, if you solve this equation, second order equation, what you will get here is one solution, it is x is equal to 2. You will get x is having some other value also, but that value it is impractical. So, you can say that x is equal to 2 volt, which gives us VGS equals to 3 volt, because x is VGS minus VT. So, this quantity VGS minus VTH we have considered it is x. In fact, if you plug in this VGS value, we can get the IDS equals to we do have IDS equals to 1 milliampere per volt square by 2. So, 1 divided by 2 here. So, that is milliampere per volt square into VGS minus VTH, and that is 2 square. So, that gives us 2 milliampere. So, we do have a current flow here, it is 2 milliampere. In fact, you can verify that if 2 milliampere of current is flowing here from drain to source, the drop getting created here, it is 3 volt, and we do have 6 volt here. So, that makes the VGS is also 3 volt, which is consistent, because if I am having VGS 3 volt, then only it will support a current of 2 milliampere, of course, assuming this transistor it is in saturation region of operation. So, that is how you can get the operating point of the transistor in CC stage, and using that you can calculate what will be the corresponding GM. So, the GM of this transistor, it is okay, let me create some space here. So, GM of transistor 2, it is we do have K W by L into VGS minus VTH. So, here also we got GM 2 equals to 2 milliampere per volt, and then the output resistance, and of course, since we do not have the equivalent whatever R pi we are having in BJT, and so the calculation here it is much simpler, and you can approximate that the gain here AV 1, it is very close to 1, and output resistance, not AV 1, AV 2 rather, second stage gain, and output resistance of the CC stage, it is 1 by GM 2, it is in parallel with R 4. Okay. So, 1 by GM 2, it is 0.5 K, and R 4 it is 1.5 K. So, that gives us I think 300 something, I do have a calculation, yeah. So, that gives us 375 ohm. So, since the gain here it is approximately 1. So, the overall gain it is primarily coming from the first stage. So, the overall gain A V overall, it remains 6 only, but then the upper cutoff frequency F u, now if I call it is F u dash, it is having two candidates to define the upper cutoff frequency. One is R O 2. So, this is 2 pi R O 2, and the corresponding load capacitance we do have C L. So, if we connect the C L here, so then the upper cutoff frequency it is 1 by 2 pi into 375 into 10 to the power minus 10, and yes, I do have calculation here. It is 4.24 megahertz. So, you may recall you can compare this frequency with respect to whatever the original pole of this CS stage it was there. So, that was F u, it was 530 kilohertz. Now, also we have to consider the other candidate of defining the upper cutoff frequency coming from this point, and that is, let me denote that by Fu double dashed, and its expression is 1 by 2 pi Rho 1, and then Cgd. So, Cgd it is 5 picofarad, and so the value of this this cutoff frequency, in fact, since this is 3 kilo and this is 5 pico, earlier we made this calculation and it was 10.6 megahertz. Now, if I compare these two poles together, of course, this is lower. So, the net upper cutoff frequency it is 4.24 megahertz. So, here also the same conclusion, it is namely originally the CS common source amplifier, it was having a gain of 6, and then it was having a the upper cutoff frequency it was 530 kilohertz. Now, we are by the virtue of the common drain stage along with the CS. So, this gain it is almost remaining the same, and its bandwidth got extended to 4.24 megahertz. Okay. Now, so that gives us the flavor of why we go for cascading CC and CD. In fact, you can try out with the other CE amplifier, which is cell biased configuration. So, this exercise we have done before. So, probably you can calculate what is its voltage gain and the upper cutoff frequency, and then you can compare this with the cell biased CE amplifier, cell biased CE amplifier along with say CC stage. So, we do have the CC stage here, and you can find that again this CC stage it is helping to extend the bandwidth. So, probably you can work out on this one. I do have another interesting example, but again due to the probably the shortage of time, I will just give you some brief and then I will be leaving it to you to solve this problem. What we have here it is what we have here it is this is the CE stage, assuming we do have a meaningful DC voltage coming here from the previous circuit, and then that is preceded by CC stage. Note that I am not providing any separate bias here for CC stage and the CE stage. So, we are assuming that whatever the current is coming from Q1, its emitter current, it is getting consumed by the base terminal of Q2. So, I should say that IB2 is equal to IE1, indicating that the current level here it is much lower than whatever the current level we do have. In fact, if you consider for both the transistors beta is 100. So, whatever the current we do have, you can imagine that this current it will be 2 order magnitude lower. So, say for example, if I consider IC1 it is 1 milliampere. So, we are expecting that IC2, if I consider IC2 is 1 milliampere, then IC1 it is only 10 microampere, and the corresponding IB1 it is only 0.1 microampere. So, we require very small current here. As a result, the corresponding R2 here R2 here we are expecting it will be sorry R1 resistance, bias resistance R1 to support this much of current, it should be definitely in maybe tens or maybe even hundreds of mega ohm. So, if you put some value of say even say close to 10 mega ohm, you will see that the corresponding current here it will be quite high. But whatever the biasing condition you can get with this one, probably you can see, and then you can find what is the IC 2 and then IC 1, and then from that you can calculate what is the R pi 2 and R pi 1. From that you can see what is the input resistance it is coming here, and you will see that by adding this CC stage, the input resistance it will be quite high. So, the input resistance expression you may recall it is coming from R 1 in parallel with whatever the input resistance we can see at the base of transistor 1, and that is R pi 1 coming in series with 1 plus beta 1 multiplied by R pi 2, and then if I consider this is AC ground. So, only this much I will be having. So, you can see that this R pi 1, since its current level it will be quite small, this will be quite high, and then even though say R pi 2 may not be having so high value, but since it is getting multiplied by beta 1, the corresponding value of this resistance it will also be quite high. As a result, this R in 1 it may be in the order of mega ohms. So, if I am having only, on the other hand, if I consider the input resistance of this stage only, the R pi 2 it may be in the range of kilo ohms, and the corresponding resistance we are getting here it is getting multiplied by 100. So, I should not say mega ohm, it will be in the order of sub mega ohms, I should say hundreds of kilo ohms. So, you can solve this problem by considering say R 1 is equal to say this mega ohm, and maybe you can consider this resistance of 1.2 kilo ohm. Sorry, you should not take 9.9 mega ohm, rather 99 mega ohm. You can consider 99 mega ohm, and then you can calculate what is the corresponding input resistance you are seeing. I think let me then summarize most of the things whatever we have planned, we have covered here. So, in this session what we have learned here, it is the usefulness of the common collector and common drain, and we have demonstrated through numerical examples, basically by considering CE and CC together, and then CS and CD together to enhance the bandwidth, upper cutoff frequency particularly getting increased by a factor of as high as maybe a factor of 10 or more. And also we have given framed one example, CE preceded by CC to increase the input resistance R in by a factor of 100. Okay. I think that is all I need to share. Thank you for listening this talk.